All right, good afternoon, everyone. Hope you have had a good week. We're almost through it, right? So today we're going to continue where we left off with this least squares solution. Last time we derived the optimal least squares weights beta have this form. So here A is a matrix that contains all of our training features, but also is augmented with a column of all ones. Y contains all our training targets, and then the beta vector we're trying to design contains the intercept term and then all the D slope terms for these different features. And so this is a nice, concise expression. And it's probably how you would actually implement it, more or less. We'll talk about that. But it's not very insightful in terms of understanding. So what we're going to do next is to try to derive some alternate expressions that are more similar to the ones we saw in the first unit that involve statistics like autocorrelation, covariance, cross-covariance, things like that. Okay, so that's our goal. And just before we get into the details, we're going to rewrite our system model in a slightly different way that's going to make our lives easier. So what we're going to do, so this is one way to write our prediction, where we're just writing in the intercept term and then all the different slope feature terms. So if you notice here, the intercept term behaves sort of differently than the rest because all these other ones multiply a feature, they're the slope terms, and the intercept term is sort of on its own. So to do the derivation, it helps to sort of treat the intercept term separately from all the other terms. So what we're going to do is we're going to define this notation B with the 1 to D in the subscript. This is going to collect the beta coefficients 1 through beta D. And so this is a vector of length D. And then that is going to be separate from the intercept term. So the overall beta vector here expressed as a row because of the transpose has the intercept and then the rest of the coefficients here. Okay, so it's just a slightly different notation. And so with this, we can express y hat just as beta 0 plus this beta 1 through D vector transpose times the x vector. Okay, so here we have, what's convenient about this is we have the x vector directly represented. We don't have this A matrix with the extra ones column that was sort of making things a bit hard to interpret. Okay, so is everybody okay with this notation? All right, so the first thing we need to do is we need to define some appropriate statistics. And these statistics are going to be a direct generalization of the ones we looked at in the first unit, except they're going to apply to vectors because we have vector-valued features instead of scalar-valued features like in the last unit. So just to start, we'll start with the mean. So here we have the sample mean of our, so remember xi is the ith vector of features, the ith data sample, and each one of these has D different coefficients in it. So here we're just averaging them across our data set, and we're going to call that x bar. So this x, this is a vector, right? This is different than what we did in the last unit when we had scalars. But otherwise, conceptually, it's exactly the same. Okay, so just to try to bridge the gap a little bit, let's remember that the ith sample contains xi1, xi2, all the way to xid, right? That's what the ith sample in our data set, the vector, consists of. And so what happens if I average the first term over the different I? What do we get? We had a name for this. So we have a collection of these scalar numbers, and we're just
Mean.
averaging them. Sample mean. Yeah, how would I write it down?
X bar.
X bar what? You got to put a 1 under it because this is the first feature. Okay, so this is the average of the first feature over our data set. Right? And we can do this for all the different features. So like the last one, if I average it, I'd get X bar D. Okay, so that's just a direct extension, a direct repeat of what we did in the last unit. So now that we have these X bar 1 through X bar D, how do you think those relate to this vector X bar? So if we look inside the vector X bar, what will we find? So is Will Barrett here?
Yeah.
Yeah, so what do you think? If you look inside that vector, X bar vector, do you find terms that relate to these?
Wait, can you say that one more time?
If you look inside this vector and look at its components, do you find terms that correspond to these?
I would think so, yeah.
Okay, so what's the first one in the X bar vector?
Wouldn't that be X bar of, it would just be X1, X bar 1?
Yes, exactly.
Okay, yeah.
Right. Okay, so I just wanted to sort of make the connection. We have this sample mean vector. I just want to say, if you look inside it, you look at the components, those are exactly just the scalar sample means that we talked about in the last unit. That's all. Okay. And we can do the same thing with our targets. Now, our targets are still scalar, so this is exactly, the Y bar is exactly what we saw in the last unit. Okay, now, moving on to the variance. So this on the bottom is what we saw in the last unit. This is how we did variance in the scalar case. Oh, question?
Shouldn't that be X bar to N, because there's N, the sum goes to N, not D?
So N is the number of samples in the data set, and that is the number we're averaging over. So like concretely, let's say I have two features, X1 and X2. I will have N samples of X1 and N samples of X2. And so I'm doing the averaging over N, and it's going to leave me X bar 1 and X bar 2. Okay. Okay, so in terms of variance, this is what we saw in the last unit, where xi was a scalar, and we said to compute the variance of x, you subtract the mean from xi, and essentially you square it. You get xsxx, okay? So that's what we did in the last unit. Now in this unit, we do exactly the same thing, but with our vector valued quantities. So xi is going to be a column vector. X bar is a column vector. And but it turns out that we actually want to look at, in some sense, all the different variances within X, but also like all the covariances across the different elements. Like how is X1 related to X2? How is X1 related to X3? How is X2 related to X3, and so on? We can build a whole matrix with all that stuff, and that is what this sample autocovariance matrix is. So you might say, well, why is that a matrix? Well, let's draw a little picture. So the first xi minus x bar, that's a column vector. The second thing, which is transposed, that's a row vector. And what happens when you multiply a column vector times a row vector? It says Mason Bruns here? Bruns, sorry. So if I multiply a column vector times a row vector, what shape of thing do I get? No, it's a matrix, right? So like this dimension has to match this one, and this dimension across the top has to match this one. Okay, so basically this is an entire matrix, and when you look at the diagonal elements of this, you will find the variances of x1, variances of x2, x3, and so on. When you look off diagonal, you will actually see the covariances between xi and xj for different I and j. Okay, so that's what's in this big matrix. Sample autocovariance matrix. Any questions on that? Okay. Then we also have the sample cross-covariance vector, and that's a vector because the first element in this multiplication is a vector, but the second one is a scalar. And so when you multiply a vector times a scalar, you just get that vector again. Okay, so this is the cross-covariance vector. And when you look inside that, you will see, let's see. Actually, let me move this right here. So what do you think we see when we look inside that vector? So let me ask this to, is Jake Borto here? Yeah. Oh, yeah, okay, all the way in the back. What do you think the first element here will be? So it's essentially going to be the first, it's like you're involving the first element of this only. Yeah, do you know what we would call it? So here is the version from last time. So it's going to have a similar notation to this, but instead of xi, when I look at the first element, I'm going to have this first guy. Yeah, so it's going to be s x1 y. And then go all the way down to the end, it's going to be s x dy. So it's the cross covariance between, like, the first one between x1 and y, second one x2 and y, all the way xd and y. Okay, so that's what these statistics are. Just generalizations of the ones we saw in the last unit. Okay, everybody good with this? Okay, so now, just like the last unit, we're going to derive just quickly some alternative expressions that will help us with the main derivation, and which may help you, in other derivations you come across throughout the semester. So we'll start with the definition of the autocovariance matrix from the last slide. And we have a quadratic form, so we can just look at the first terms, and then we can look at this one times this one, that gives us this, and then we can look at this one, and then finally these. Okay, and of course there's an average applied to every one, so that's where we get, this is the first term, this is the second term. Essentially I can move anything out of the average that does not depend on I, because multiplication is linear, so I can move that sum in. And how can we simplify this? Anybody recognize what that is? Just x bar, exactly. It's the vector x bar, so I'm going to put an underline on the bottom and on the top. And then we have exactly the same thing here. And so now you can see this is like an x bar transpose, another x bar transpose, and another one. And so a couple of them cancel. So we have the first term, and then we have minus x bar transpose. Sorry, I'm getting a little sloppy here. Okay, so this is, we saw the scalar version of this last time, where it was like this, but everything was vectors. Okay, any questions on that? Okay, so we can do the same thing for this quantity. So we have the first term here, we have this inner term here, we have this outer term here, and we have the last terms here. And now, in this case, we can simplify by noticing that this is y bar, right? This is x bar. And so the last three terms are x bar, y bar. And so two of them cancel, and we get the sum minus x bar, y bar. Okay, so these are just useful things that we can use in the derivation coming up. Are there any questions so far? Yes.
And just to make sure I'm following correctly, the summation is of everything following it, not just the summation of the two terms and then subtracting a separate term, correct?
Are you talking about this summation or one?
The two blue
Like this one?
No,
Oh,
the
oh,
far
this.
right side of it. Yeah.
Oh, so actually either way is fine. I think the simplest way to think about it is think about this as a unit. But the reason why even the other way is okay is because if this averaging operation is applied to this, because that is a constant with respect to I, it just stays the same.
I was just wondering because that would, okay, never mind.
Right? So either way it's the same, but the way that I would like you to interpret it, the easiest way is like that. Because often you tend to see this, and then you can write this in terms of these statistics here. Like by just moving this to the other side, you can see that this sum is this covariance vector minus the product of the means, or plus the product of the means. Okay. Good questions. All right, so any more questions on this page? Okay. So now we're going to do this derivation. And this derivation, I'm going to go a little bit fast because it's exactly what we did last time. And rather than spending time on these little details, I want to spend more time on conceptual things today. So, but let's just go through it. Here, there's a small typo. This should just be the beta vector here. Okay. So, so the technique that we always use to solve these problems, to minimize RSS, because RSS is a continuous convex function, we're going to take the partial derivative with respect to each of the coefficients and set that to 0. We'll get some expression and then we'll have a whole basically coupled system of equations. We'll solve those for the coefficients. So that's exactly what we did. We've done it twice now. This is the third time we're doing it. Okay, so RSS is exactly this. If you remember, this whole thing here is just minus our y hat I. We're just expanding it now in terms of the beta and the part that involves the features. The intercept and the part that involves the features. Okay, so the next task is to take the partial derivative of this expression with regard to beta naught. So it's just as before, we saw we can move that through the sum due to linearity, and then we apply the chain rule to this. So we're going to get 2. Maybe I'll put the sum here. We'll get, oops, that should be n. Okay. We have 2 times the sum of this quantity in the parentheses, and we'll just, we'll use a, yeah, we'll do that. Beta 0 minus x bar I beta vector 1 through d. And now we have to take the partial derivative of the thing in the parentheses with respect to beta 0. And what is that? Minus 1, right? So I just put the minus in front of here. Okay, so that's the first part. And now we have to do it again to the same expression, but we're going to take the partial derivative with respect to beta j. And so the beta j is one of the terms inside this beta vector. So to draw it out, let's replace this vector product here with the summation version of it. And just like we talked about last time, j has a special meaning here. J is a fixed quantity. I cannot use j again to represent this sum because I would be using the same variable to mean different things. So I'm going to use something else. I'll just use j prime. Okay, so it's the regular sum but with j prime. And now you can see that when I'm focusing on a particular beta j, there's only one term in this sum that matters, and it's the term that is xij beta j. All the other terms involve different betas that are different from this beta j. Okay, so when we do the chain rule, as before, we get 2 times the sum times this same thing inside the parentheses. And now we take the derivative with respect to, of this with respect to beta j, and what do we get?
Minus xij.
Minus xij, exactly. So put the minus here, xij there, and yeah, that's all we need. Okay, so just as we did last time. Okay, so, and now we're going to, again, use the same steps as last time to simplify this. So we have essentially we want to turn these into averages because then we can plug in our statistics. So we want to change the -2 to a 1 over n, so we can multiply both sides of this equation by -1 over 2n, and that will give us this. And then we can expand this sum into 3 different terms, this one, and this one. And just like on the last page, we recognize the first is y bar, we recognize this term as x bar transpose. We can think of this as separate from the beta 1 through d because this does not have an I dependence. So that's why we can make this substitution. And finally, we now have an expression for beta 0. All we have to do is bring beta 0 to the other side, and we get that beta 0 is y bar minus x bar t times the beta vector 1 through d. Okay. So this may look familiar to what we saw back in Unit 1. It is very similar. We'll do a comparison in a few slides. Okay, so we've solved for beta 0 in terms of the other coefficients. Now we have to solve for the other coefficients. Any questions so far? Pretty good? Okay. All right, so now we're going to start with this equation here. Multiply both sides by 1 over 2n, so that's going to turn this into a 1 over n. And as a result, we will get this. Okay, so this, as before, we can split this into 3 separate terms. Here's the first, here's the second, here's the third. Just a note, like in this middle term, we applied the average over I here and renamed that x bar j, because this guy is just, it's the average over our data of x, the jth feature, xj. So that's why we get x bar j. Yeah, everything else is just direct algebra. To go further, we can plug in this expression for beta 0, and you can see what's going to happen is we're going to get x bar j y here, and then we're going to get x bar j times this thing here. Everything else is the same. Okay, and now here's a similar step to what we did before, maybe a counterintuitive step. Here we have a scalar quantity, right? This is just equal to scalar 0. We're going to actually extend this into a vector and extract the jth element so that it is equal to the original scalar. So to do that, I'm going to extend this into a vector, column vector, extend this into a column vector, this one, and this one. So if I have xij and I extend this by looking at all the different j terms, those are all my different features, I get xi, right? Does that make sense? I'm stacking all the j's on top of each other. And now I'm just going to extract the jth term of that, which of course gives me this. Do you see why this is an equality? I made it into a vector such that if I extract the jth term, I get what I started with. Okay. I'm going to do the same thing here. X bar j, we said, is the jth term of the x bar vector. And same over here. And finally, this is just like the first case. Okay, we're almost done. Maybe you see where we're going. Take a look inside these square brackets. Does this term here look familiar? It's like something we derived a couple slides ago, right? Yeah. So that is going to be the is going to be the S vector xy. This is the cross covariance vector. That's what that is. And then the rest of this stuff, notice that they both have beta on the end, so I can actually move this inside those parentheses if I want. And then the result is something multiplying beta 1 through d. Does anybody recognize what that something is? It's the big S matrix, SXX. Okay. And let me put an underline under it because it's bold. Okay, so we find that when we take the derivative with respect to beta j, that the jth column of this vector must be 0. But we said earlier, actually we need to do this for all, this needs to hold for all j. So that means that it's not just any particular j that this needs to hold for, it's actually all j. So that means that this entire vector must be 0, which is this expression. Here I have the 0 vector. Okay, so we just basically proved that. And we're almost done. How do I finally find beta 1 through d, this vector? Let me ask, is Ayman Iraqi here? How do you pronounce it? Ayman, sorry. Okay. Okay, when you say over, what do you mean? Okay, you have to be careful because we have matrices now. So when you have scalars, okay, so this is what I want to say. So when I have scalars b and a, b divided by a, we can write that as a inverse b, or we can write that as b a inverse, right? When they're scalars. When they're matrices, we cannot do this because the order of matrix multiplication matters. Matrix multiplication does not commute, meaning you can't swap the order of matrix multiplication. So that's why we have to be a bit more careful. We can't just divide by a matrix like without knowing where it lives in the order. So the way that I like to think about this is take this original equation and multiply both sides by SXX inverse, that matrix. Multiply it on the left. So if I multiply this on the left, SXX times 0 is what? 0, right? Actually, sorry, there's an inverse there. So SXX inverse times 0 is 0. And then I'm going to get SXX inverse SXY. And then I'm going to get minus. So now if that matrix is invertible, then the inverse cancels the original matrix and we'll get beta 1 through d. So I'm going to assume here if this inverse exists. So now we can finally see I have 0 equals this. So now I can just move this to the other side. And I have that the S inverse is on the left of the S vector. Okay, so that is the equation for the least squares version of the remaining coefficients. Maybe I should put this in the box because it's important. Okay, so that's that derivation. Like I said, it's stuff you've seen before, so that's why I went through a little bit quickly. Everybody okay with what we've derived? Okay, great. So let's take a step back and look at what we've derived. So if I stack the beta 0 coefficient on top of the other ones, according to the equations on the previous 2 pages, the total least squares beta has this scalar element sitting on top of this vector. Right? So that is, I'm just putting those things together to make the complete least squares beta vector. Everybody okay with this? Let me just maybe make a picture. So there's a scalar sitting on top of a vector. Okay. Now, let's think back to what we did in Unit 1. So in that case, we had a very similar problem, but it was a little simpler because xi was a scalar, non-bold. X bar was a scalar, again, non-bold. This matrix autocovariance was just a variance, and this vector cross covariance was just a scalar covariance, cross covariance. And if you remember the equations we derived, in that unit were the following: y bar minus x bar sxy divided by sxx. Now those are scalars, so I can do that. And then down in the second term, this is only a two-term vector, I had sxy divided by sxx. Okay. So when you compare them, now you see that these are, the top is just the matrix extension of the bottom. Okay. They agree completely. It's just if you turn these things all into scalars, you get exactly that. Okay, so we've just sort of repeated this with a little bit more work, a little bit more sophistication. But the intuition is the same. Okay. All right, any questions on this? Everybody good with this? So now we have basically some sort of interpretation of what these beta coefficients are. We see the statistics involved, the covariance matrix of the features, which tells you how correlated the different features are to one another. Then you have this cross covariance, which tells you how correlated the features are to the target. And then you have the sample means. And that's what's all coming together to create these least squares coefficients.
Both of those are scalars, you said? The ones in the...
Down here, everything is scalars. Yeah, these are all scalars. Up here, the bold ones,
Yeah.
you know, capital bold is matrix, lowercase bold is vector. Okay, great. So, so that's all we have for this. We can move on to a next topic if everybody's good. Okay, so let's talk a little bit about how we implement this. So there's actually several options we could use. Some are better than others. So one approach is to take this most concise expression that we have and implement this directly in Python, or in particular in NumPy, because NumPy has these linear algebra routines we need. So to do this, for example, you would start by creating this ones, a vector of ones. You have to make it the right length. And so this is how you would do it with NumPy, np.ones, and then you tell it basically the dimensions. You're making a matrix of ones that has n-samp rows and one column. And then we've already made our X matrix, and now to make this A matrix, you use np h stack. So it's like a horizontal stacking between those two quantities, and you get your A matrix. And I'm not showing it here, but with like one more command, you can do this matrix inverse and so on to get the betas. So the reason why I'm not spending a lot of time on here is because this is not how we want to do it. So the problem with this, there's several problems with this. It's basically computationally slow, as well as subject to numerical precision errors. The inverse of a matrix, the computation is cubic in the dimension of the matrix. So that's not great. And just even, we have a whole bunch of matrix multiplies we have to compute. That takes time itself. So if you want to solve this, a much better way is to use specific algorithms that have been derived by experts in linear algebra to do that task of solving a least squares problem. And so here we have NumPy, linalg, least squares. You basically just tell it the matrix and the vector, and it will solve it for you. And this method is only quadratic complexity rather than cubic. So this is a much better alternative. It avoids a lot of unnecessary work, and numerically it's more precise as well. Yeah, so that would be a better alternative. However, we're not going to do that either. The most convenient thing for us is to use the linear regression command within the scikit-learn package. And part of the reason we're going to do this is because this scikit-learn package, the way that it does linear regression is the same interface that we're going to use for classification, all sorts of things throughout the term. And once we learn this little interface, it's very powerful because we'll just use it over and over again. Okay, so the way the interface works is the first step is you define or instantiate this object, this regression object. You go to the linear model library in sklearn, and you say, make me a linear regression object. So this object has a bunch of containers for data and coefficients and stuff, but it also has functions attached to it. And so the first one we're going to use is the fit function. You give it the matrix of features, you give it the vector of targets, and you do fit. This does least squares fit, and it will compute the beta coefficients, and it will store them internally. It will not spit them out. It will just quietly store them internally. If you want to see them, you can. There's another command you can use. You can look at the coefficients, and you can look at the slope, and you do separately. But we don't actually even need to get access to the beta coefficients if what we want to do is prediction. If we want to do prediction, in other words, we want to execute y hat is a beta least squares. I want to take my features, take my least squares coefficients, which I computed, and compute my predictions of the training targets. I can do that in this command right here, the predict command. You tell it predict based on this matrix, and it knows these coefficients internally, and it will output this y bar here. Okay. Is everybody with me so far and how we're going to use this? And that's pretty much it. Everything else is stuff we've seen before. So to compute RSS, you take a vector difference between the y hat and the y, you square every element, you sum those all together to get RSS, and then you can turn RSS, you normalize it, and you can turn it into R squared. And R squared is how we interpret how good the fit is, right? So we'll print out the value. And in this case, this is this diabetes demo. We find that the R squared is 0.51. So is that good or bad? Let's see. Is Kartik Guru Subramaniam? Yeah. What do you think? Is that good or bad? Okay. I like it. Yeah. So it's like halfway between 0 and 1. So it's definitely not good. It's definitely not bad. It's just somewhere in the middle. But it's a reference. Okay. So that's how we can do this with sklearn. You can, of course, see this in the demo. You will have an opportunity to play with this in the lab too. Any questions on how we do it here? Okay, great. So now let's step back and consider what we've done in this unit compared to the last unit. So in this unit, let's say in the last unit, we did simple linear regression. And by simple, we just mean that we used one feature alone. And that gave us a prediction. And we could do that for our diabetes data set, right? We have all these different features. We could just use one at a time. We'll get a whole bunch of different predictions of different quality. And we'll try that in just a moment. But the thing we did most recently is we did multiple linear regression, which is when we use multiple features. So here we take all the features in our data set, stack them all together. We jointly predict the targets based on all those. And so you might ask the question, well, which one is better? So let me just start by asking you to raise your hand if you think multiple linear regression is always better. Okay. Raise them a little higher. Okay. And how many of you guys think simple linear regression is always better? No one? Awesome. How many of you think that sometimes multiple might be better and sometimes single? Okay, a lot of people. So That's actually a great answer because I was a bit vague in my question. So let me sharpen my question and ask you again. So if my goal is to minimize the RSS on the training data, and that's my only goal, is multiple linear regression always better or at least as good as simple? How many people think yes? Okay, how many people think no? Okay, so the answer to that is yes. If all we care about is minimizing our training error, multiple linear regression can be no worse than simple linear regression because it has more data, it has more information, and it's not doing anything wrong with that information. It's not making any mistakes. It's using all that information in the optimal way to minimize RSS. So if that's our goal, minimizing training RSS, multiple linear regression will always be at least as good, usually better, almost always better than simple linear regression. Okay. Now, there is a case where sometimes simple linear regression could win, and that is when, instead of measuring our performance on the training data, we have some other test data set. And that will actually be the subject of the next unit. So I'm not going to delve into that now. I'm just acknowledging that some of you may have answered correctly, knowing a little bit about that, peeking ahead in the course, when I first asked you which one is better. Okay, so let's do a little experiment with our diabetes demo. So we're going to have a for loop here. And in this for loop, we're going to do simple linear regression for each of our features individually. And we spit out the results. So this is for our first feature. This is the R squared. This is the slope coefficient and, sorry, the intercept beta 0, and then this is the slope coefficient. So the thing to pay attention to right now are the R squared values. So when we look through this list, the very largest one that we find is 0.34. And remember, with multiple, it was 0.51. So this is verifying what I was saying, that when you use them all together, you're going to do better, or at least as good as using individual ones for the purpose of minimizing our training RSS. Now, some of them do terribly. Like, look at this second one. The R squared is 0.0018. It's barely better than a trivial estimator, right? That's just the best you can do with that feature alone. It's just not a very good feature alone. But you put all these features together, and you can do better than any of them alone. Okay, so again, the moral of the story is, in general, least squares linear regression performs at least as well as least squares simple regression. And maybe I'll put the caveat here to minimize training RSS. So that has been our goal and our only goal this whole time. Yes?
So with the way that potentially your S-curve might work out, is there a possibility you could improve your multiple R squared by simply omitting potential factors that are below a certain threshold in their single linear regression?
It turns out if our goal is to minimize training RSS, the answer is no.
I meant, sorry, when applying it to testing, but that's...
Yes.
Yeah, that's
When applying it to some other test data, and this is the subject of next unit, so I don't want to dive too deep here, that is exactly an issue. And in that case, we have to be more careful, and we want to make sure we're not using features that are distracting us, that are putting in more noise, so to speak, than information. So that will be a big topic of discussion soon, but right now, we're not quite there yet. All right. Okay, any other questions on this? Excellent. Okay, so, and then here's just a little bit more, in practice, we don't usually just care about the training data. We actually care about what's going to happen when I apply this in the real world, in the wild. So just as an example, to see what happens for this diabetes data set, what we can do is we can take the total data set, 442 samples, and we can partition it into two. We can split it into two. For the training data, let's take the first 300 samples, and for the test data, let's take the remaining 142. And so what we do is, here you can see for the training, we extract just a subset of the total data in the data set, and for test, a different subset. And then let's do the fit with the training alone. Let's predict the training targets. And then separately, we can predict the test targets. And we can, with a few more lines, we can compute the R squared on both. And this is sort of what you typically find. The train R squared, 0.51, not so different from what we found here, right? Even though I'm using a bit less data. Now the test R squared is close, but not quite as good. So something about that test data, even though it should be statistically the same, it's just, a little bit harder to predict, or at least, what we learn on the training doesn't help us quite as much on the test. Okay. So this is something that, again, we're going to discuss this much more in the next unit. But for now, it's just sort of a taste of what you might actually do in practice. Okay, great. Any questions on this? Okay. All right, so now let's talk about kind of a different topic. So until now in the course, for our feature data, we've only considered what we call ordinal quantities. Ordinal numbers are numbers that are ordered. So like the numbers 0, 1, 2, 3, 4. Those are ordered in that 0 is less than 1, 1 is less than 2, 2 is less than 3, and so on. But sometimes when we do prediction, the feature data is not ordinal. It could be categorical. Categorical just means there's categories. So for example, let's say we want to predict the miles per gallon of a car given horsepower. So miles per gallon Y given horsepower X1 and the brand X2, where in this case the brands are Ford, Honda, BMW. So notice that it's very difficult to say, with confidence that you have an order in there. Ford is less than Honda is less than BMW, right? It's not really possible to say that. Maybe in particular ways there's some ordering, but in general, at least for predicting miles per gallon, it's not really clear what the ordering would be. So we don't want to make an ordering. We want to avoid making an ordering. We don't want to pretend that like Ford is 1, Honda is 2, and BMW is 3, and then do the same linear regression we've been doing. That would not work well. So instead, we're going to use a trick called one-hot coding. And the main idea is to code brands as binary vectors. So that might sound weird, so let me show you what I mean by just an example. So look at this little table. So remember that the brand is X2. So instead of thinking about X2 as a real number, think about it as a binary vector of 3 numbers, such that whenever you have a Ford sample, so we're actually going to expand X2 into 3 different things. We'll call it, X2 soup 1, X2 soup 2, X2 soup 3. So whenever you have a Ford, you're going to put in the binary vector 1, 0, 0. Whenever it's a Honda, it's going to be 0, 1, 0. Whenever it's a BMW, it's going to be 0, 0, 1. Okay, so now you can see that there's no, ordering between Ford, Honda, BMW. They're just different. So now, instead of the linear model having a beta 2 x2 term, we actually expand it like this. You can see we have 3 different coefficients, beta 2 multiplying this, beta 3 multiplying this, and beta 4 multiplying this. Okay, so is it clear what we're doing in this case? So whenever we have a brand, instead of representing that by a single real number feature, we're actually going to represent it by 3 feature values, which will either be 0 or 1 in a particular pattern. Okay, so now that I have this, I can use the same techniques that we've developed until now without any issue. Yes?
What difference it makes when we call it as X3 and X4 instead of calling X2, 2, X2, 3 and all?
No difference. It's just I thought it would be maybe a little bit clearer because it starts with X2 that we're just somehow expanding this into like 3 parts. But yeah, I could have called it like X3, X4, or sorry, X2, X3, X4.
Because the beta coefficient is similar to the X.
Yeah. I think if I called this X2 and the brand originally was X2, for me, there would have been a confusion, so I did this instead. Okay, so, all right, so that's the approach. Any questions about what we're doing, or is that pretty clear? Okay, so let's see why we're doing it. Let's see what happens if we do this. So when you look through your data, anytime you have a Ford sample in your data, you're going to essentially put a 1 here, a 0 here, and a 0 here. So because of there's zeros in those last two terms, those terms are just not even, they just fall away, right? And this term just turns into a 1. So essentially, all the Ford samples take this form. There's a beta 0, there's a beta 2, and there's a beta 1 x1. Okay, now let's think what happens to the Honda samples. So in the Honda samples, these are all going to be zeros, these are always going to be ones, these are going to be zeros. So essentially, these ones go away, and you just got a beta 3 there. So that gives you this. And finally, with the BMW samples, not surprisingly, first two go away, and you get a beta 4. Okay. So this is what happens when you do this one hot coding. So essentially, you get this new linear model that has the flexibility to use a different intercept term for each one of these categories. So all the Ford terms, they can have their own intercept. The Honda terms can have a different intercept, and the BMW terms can have a different intercept. But they all have the same slope. Okay, so is it sort of clear what's happening here? Okay. So that's sort of the main interpretation of this. And just to be clear, I'm going to put in the title, this is one hot coding of the intercept. And this is the standard one hot coding. This is the way that it's usually described. It's not the only way we can do one hot coding. Before we move on, are there any questions on this here? Okay, yes.
Why is it that each of the brands are restricted to having the same slope? Is it because there's no particular bias between the different brands? Or?
Yeah, it's sort of like we set out using this idea of expanding x2 into these binary vectors, and we just said, let's see what happens if we do it. And this is what happens. And it's similar to what we saw in the usual case. If I have a horsepower x1, then I have a beta 1, and that's what we have here. It's nothing has changed with that.
Okay.
So what's changed is really how the intercept terms are handled. Okay. So let me show you a different way you can do this. So here's the motivation. We want to predict, again, mile per gallon of a car, given its horsepower and brand, same brands. But now, let's say you think these guys at Ford, they kind of cheat when they measure horsepower. So when you're looking at the specs of a Ford and it says it's 100 horsepower, if it was a BMW, probably they wouldn't have said that's 100. They would have said it's like 80 or something. So now the idea is, okay, I want to treat the slope coefficients differently depending on what brand it is. So we can do that. I'll show you how we do it. We use exactly the same coding scheme where we essentially expand x2 into these binary vectors, but then we use it in a slightly different way. So here's how we can use it. So notice these terms. So for example, if I have a Ford, then I'm going to get, this is going to be a 1, this is going to be a 0 and a 0. Right? So when I have a Ford, I'm going to have this. All my Ford samples will look like this. On the other hand, if I have a Honda, this will be 0, 1, 0. So those go away. And I'm going to have a beta 2 x1 and a beta 0. So notice what happened now. I get to use a separate slope coefficient for all the Honda samples that's different from the Ford slope coefficient. Likewise, with the BMW, I get to use yet a third slope coefficient. Okay. So So this is just another way to use one-hot coding where you one-hot code the slope. So just showing you the flexibility of this approach. This is not the standard approach, but it is something you can definitely do. Okay. All right. Any other questions? So we're almost done. Yeah, last slide for today. So there is a little bit of an issue or potential issue with the one-hot coding of the intercept, the first version we saw. So, and you may have already noticed something weird about it. So, does it look like there's maybe a kind of a redundancy here? Right? Like, how many different coefficients are we using to represent the intercept?
You basically created a fluid intercept because you got 4 different things
Right.
that are-
We have 4 different coefficients that are modeling 3 different intercepts. So there's a certain redundancy. And you might say, that's fine. But actually, it has a consequence. And the consequence is that A matrix, or in particular this A transpose A, becomes non-invertible. And remember, that was one of the things we said, in order to get the least squares solution, that matrix should be invertible. So now when you do this, it becomes non-invertible. And let me try to prove this to you, proof that it's non-invertible. And the proof is just going to, again, focus on this simple case of 3. I'll just prove it in this case, but it holds in general. So this is what we have with our one-hot coding scheme. In this case, our beta vector has 1, 2, 3, 4, 5 terms. And when you look at the rows of A, they will have this form. So always, the first column maybe is always 1, right? So that's, no matter what, that's a 1. The second column of A will be filled with the x1 features. So we have these, xi1. The third column of A, for the Fords, it will look like this. Or, the remaining columns for the Fords will look like this, for the Hondas like this, and for the BMWs will look like this. So here's the thing. I can be sneaky, and I can construct this very weird beta vector that causes problems. So let me show you how it causes problems. This beta vector, if I multiply it by my A matrix, imagine if I multiply this times this, I'm going to get 0. Because what I'm going to get is I'm going to get 1 times -1. That's a -1. That's going to be, we're going to add 0, add 1, so I get a 0, and adding zeros. So this will give you 0 in every single entry in the output vector. So now if A times beta is 0, I can multiply both sides of that equation by A transpose. And I have this, A transpose A beta is 0. And beta is not a 0 vector. So here's the deal. The whole thing with invertibility is that if you have a system with an input, invertibility means when you look at the output, you can figure out what the input was. Right? Here I have a system where I have input this beta, and I got 0 on the output. And I would have had the same output if I put in 2 times this beta or 3 times this beta. I can never recover that from the output. So I've lost information when I put this through this A transpose A matrix or system. So this matrix is not invertible. So this is sort of a proof. Whenever you have a matrix and you multiply it by a non-zero vector, if that gives you 0, it's not an invertible matrix. Okay, so this is just a proof that this happens. So how do we fix it? It's actually pretty easy. We simply omit, there's many ways to do it, but one way is you simply omit this last column. It's enough just to use those 2 columns for your one-hot coding, and that will get rid of the problem. Another thing we'll talk about later in Unit 4 is we can come up with a more robust method that doesn't care if the A matrix or A transpose A is non-invertible. That's another way around this problem. But we'll talk about that later. Okay, so that's all I have for today. Hope you guys have a great weekend, and we'll start the next units next time.